Let's see. All right. So welcome back. Hopefully everyone had a nice weekend. It was certainly a nice sunny weekend. So that was nice. So does anybody have any 10.3 questions for me? Yes, sir.
Yes. I was wondering if you could do number 43 specifically. I figured out the like S sub n.
Yes.
But for A sub 5, A sub 10, A sub 30, is there an easy way to just do those?
Okay, let's take a look. So you said 43?
Yes.
Uh-huh. So 43. So it says F is 0.25. And then M is 200 milligrams. Okay, so let's read what it says here. Suppose you take a dose of M milligrams. Okay. Fraction of the medication that remains in your blood 1 day later. Okay. Just after taking second day, the amount of medication in your blood equals the sum of the second dose and the fraction of the first dose. Yep. Okay. Yes. Okay. Yep. Very good. So maybe let's just write a couple of them, right? Just so we get a feel for it. So what are we talking about when we say A sub, let's say, 1? And I'll change my pen if I can here. So it's pretty bad. Okay, so what's A1?
200.
Yeah, it's just M, right? And in this case, that's just 200. So A1, 200. What is A2?
50.
Yeah, so A2 is going to be 200, right? Plus the amount that you have left from the first day, which is 200 times 0.25. If you like, that's a fourth, correct? And so what's A3? So that next day you take a new dose of 200, plus you have 200 times 0.25. Then you have plus 200 times 0.25 squared, which is the amount that's still in your blood from the very first day, right? So the first dose is here, and then it's here, and then it's here, right? And they're saying, okay, and we get the idea. Do you agree that this is geometric? So this is a geometric series, and what is my R in this case? So what's the ratio, so to speak, that we multiply by every time to get to the next term of the series? Yeah, 1/4 or 0.25, whatever the case may be. So I'll just say it's 1/4. And then what's A? A is typically just the thing you start with, right? And in this case, it's 200. So we have A and R. And the question is, okay, so what is some of these values that they ask for? Let's see. They say, for the given values of F and M, calculate A5, A10, A30, and then the limit is n goes to infinity. Okay, so this is geometric, and there is a formula for like the nth term of a geometric series. So let's see, where's the actual formula at? Here it is. Okay, so we can calculate, this is on page 663 of your book, that the nth term of a geometric series is equal to A times 1 minus r to the n divided by 1 minus r. And if you watched the lecture already over this, I get to this point when I'm proving the convergence or divergence of a geometric series. And then I take the limit of this thing as n goes to infinity. This thing, if r is in between -1 and 1, this thing goes to 0, and you're just left with a over 1 minus r. So if you watch the lecture, that's where that comes from. But if you just need to know what's the nth term, which is what we need to know right now, then this is what you need. So what are we looking for? It says like figure out the 5th term, the what, 10th, was it?
Yeah, 10 to 30.
Yeah, the 5th, 10th, and 30th. So if I wanted to know like what's A5, then my A in this case was 200. And then I've got 1 minus R, which is a 4th, to the nth power. Now I need to be a little bit careful here. Let me make sure that I'm doing this right. So S sub 1, yeah, it's good. So I do put 5 here. So 5, and then this is just over 1 minus 1/4. Now, that's a little messy, but certainly your calculator could do it, correct? So just plug that in, see what you get. Similar though for A10, that's just 200 times 1 minus 1/4 raised to the 10th divided by 1 minus 1/4, and so on. And then the question is, well, what's the limit as n goes to infinity? Well, that's the true sum of the geometric series. And we know that the sum of the true geometric series in this case would just be, I don't know if they have a nice name for it, but if I just wanted to add up all of them, then I am going to just take A over 1 minus R. And that's the sum of a geometric. In this case, my A is 200. And my R is a 4th, so it's just 200 divided by 1 minus a 4th, which I suppose I could calculate if I wanted to, but that's it. Does that make sense?
Yes, thank you.
Cool, yeah. Other questions? 47? Sure.
Okay. 47. Right, each repeating decimal first as a geometric series and then as a fraction. Perfect. And we're starting with 0.3 repeated.
Yeah, that's fine. Okay. 0.3 repeated, otherwise known as 0.3333, and so on, could be written this way. It's also equal to, well, 0.3. Let me write it this way first, and then I'll write it a different way. It's 0.3 plus 0.03 plus 0.003 plus 0.0003, and so on. Agreed? Okay, so, but 0.3 is just 3 divided by 10. What's 0.03? Yeah, it's 3 over 100, right? And 100 is 10 squared. So I could write this as 3 over 10 squared. Plus, and I think we get the idea now, this is 3 over 10 cubed, 3 over 10 to the 4th, and so on. So now we see that, oh, 0.3 repeated is a geometric series. So the question here is, what is A and what is R for this geometric? A is typically just the first term. And in this case, the first term is 3 over 10. So that's my A. And then R is what do I have to multiply the first guy by each time to get the next guy? 1/10. That's right. So 1 over 10. And so now if I wanted to sum up this geometric series, I just need to take A over 1 minus R. And that's the sum of the geometric. Provided, of course, that R is in between -1 and 1. If it's not, it diverges. And in this case, what is that? A is, we said 3 over 10. R is 1 over 10, so it's 1 minus 1/10. And we get 3 over 10 divided by 9 over 10, which is otherwise known as 3 over 10 times 10 over 9. 10s cancel, and we just get 1/3. Which of course is what 0.3 repeated is, right? It's a third. Now, here's a really fun one. Did I talk in the lecture, did I talk about 0.9 repeated?
0.09.
I did 0.090909. Okay, that's not as fun. Let's talk about 0.9 repeated for a second because this is really interesting. So take 0.9999 and so on, otherwise known as 0.9 repeated. Agree or disagree with what I'm about to write? That equals 1. What's that?
I disagree.
Disagree. Does anybody agree with that? Well, it either is or it isn't. So I'm going to give you maybe 3 different reasons why that actually is true. That's true. 0.9 repeated is 1. Okay, here's one way to think about it. Take the numbers 2 and 3. If I average them together, what do you get? 2.5, right? Which is neither 2 nor 3. The average of 2 different numbers is never one of the numbers. Do you agree? So if I take 4 and 6, the average is 5, which is neither 4 nor 6. Agreed? Okay, take 0.9 repeated and 1. Average them together. What do you get?
1.
Well, either you could say, well, 0.9 repeated? Because is there a number closer to 1 than 0.9 repeated? Well, there is no such thing as a closest number. There's always numbers in between any 2 numbers, right? The average of the 2. So if you're saying there are no numbers in between 0.9 repeated and 1, they're the same number. Just let that sink in for a second. And now let's do something else. Yeah.
What about a number like less than 0.99? That's like the closest to 0.99. That's not. Wouldn't that be 1 as well?
What? Okay. Yeah. Good question. I like how you're thinking. It brings up an interesting point. So what is the number that you think is closest to 0.9 repeated?
Probably 0.99 and then at the end like.
But as soon as you decide that it's not 0.9 repeated, like let's say it goes 0.999 and it does some 9s for a while, and then you say 8. Well, what about the one with an 8 and then a 1? Or an 8 and then a 2? That's closer. So there's no closest number to 0.9 repeated. There's always space in between, always. So you could average them and get a number that's in between. What I'm saying is you can't average these two numbers and get a number in between because there are no numbers in between, which means they're the same number. Okay, if you don't like it, which that's absolutely fine that you don't like it, let's do something else. Let's think about it this way. Well, let's subtract. Because if they're different numbers, then something should be left over when we subtract. So let's take 1 minus 0.9999999. What's left? Yeah, no 1.
No.
You never get a 1, right? Because if you ever got a 1, then that would mean that there's nothing else behind it. So it's 0, 0, 0, 0, 0, 0, 0. It's 0. So they're the same number. Okay. If you don't like that, let's think about the geometric series. Well, here, for example, I just said nobody seemed to have a big problem with 0.3 repeated being a third, right? What's a third times 3? 1. Oh. What's 0.3 repeated times 3? 0.9 repeated, correct? Oh, wait, but that's 1. Interesting, huh? Okay, so 0.9 repeated is 1. There's no difference between those two. Just two different ways of representing the same number, which isn't really that shocking to us. We do it all the time. Like, for example, 1/2, we say that that's equal to 2/4, and we don't seem to have a big problem with that. So it shouldn't be that weird for us that there's two different ways of saying 1. We could say it's 1, or we could say it's 0.9 repeated. It's the same thing. Everybody feel good about it yet? Any questions before I move on? Yeah.
What about with numbers bigger than 1, like in question number 50, it's 1.25 repeated.
Okay, let me see. Number what?
50?
50? Yeah, 1.25. Yeah. Okay, so they're doing something to kind of trick you a little bit, but just don't fall for it. So 1.25 with the 25 repeated, right, is we could write it as 1.252525, and we get the idea. But the other way that I could think about this is, let's just take the 1 part and set it to the side. And then we'll just look at the plus 0.25 plus 0.0025 plus 0.00025 and so on. So this guy, just ignore him for a second. The rest is a geometric series. This one, I'll just add on at the end.
Would you use that as your A?
No, because I'm just gonna like set him. It's kind of like, just forget about him for a second.
Okay.
He's there, but I don't care.
Gotcha.
Everything else is what I care about. That's the geometric part. So now I would just say, okay, A is 0.25. R is what in this case? Yeah, it's 1/100. And so now I could say that forgetting the 1, everything else adds up to A over 1 minus R. But then I'm going to have to add the 1 back in to get, so this is going to give me all of that stuff. And then the 1 is hanging out waiting for me to do that. Does that make sense? Okay, this is why when we talk about, in algebra class, you first learn about rational numbers and irrational numbers. What's a rational number and what's an irrational number? Or what's the difference? In your algebra class, what do you call What defines a rational number? Not necessarily whole. So like, is a half a rational number? Yeah, a half is. Is this thing a rational number? 1.2525252525.
Isn't it a real number?
All of them are real. Rationals and irrationals are real numbers.
The exact numbers or?
Okay, so I'm taking it that you don't remember.
No.
That's okay. So you'll remember this little saying though. Rational numbers are numbers whose decimal expansion either terminates or repeats. That should sound familiar. It either terminates, meaning it's just a finite length, like here's a rational number, 0.023. That's rational because it terminates in its decimal expansion. And in fact, I could write it as a fraction. What would it be? 23 over what? 1,000. See, I can write it as a fraction. That means it's rational. Rational also just means you're a fraction. You're an integer divided by an integer. So any integer divided by an integer is a rational number, but we also say that it's something that never, either it terminates or it repeats. So anything that has a repeating pattern is a fraction. And how would you figure out which fraction it is? Well, it's a geometric series. So add up the geometric series and you get which fraction it is. Does that make sense to everybody? And then we have all the other numbers that are called irrational numbers, where it never terminates and it never repeats. Like pi is an example of an irrational number, right? It never has a repeating pattern. Those numbers are not fractions, and they cannot be written as a fraction. So that's where kind of like this whole idea comes from, is the ones that repeat, you could use a geometric series to figure out exactly what fraction that represents. And they all represent something because they're all geometric series. Sound good? Okay, so interesting little discussion, but it is interesting to know that 0.9 repeated is 1. I always think that that's kind of a fun fact to share. And in a similar sense, like 1.9 repeated is 2, right there. Or how about 1.1 like this? What if I had like 0.129 with just the 9 repeated? That's really just 0.13. Yeah.
Would you do the same tactic there as just set the 0.12 aside?
Yes. And as soon as I get to basically 0.009 repeated, that is 0.01. So I just add a 1 here, and I get 0.13. So anytime you have a 9 repeated, you could just round that all up to the next guy, because they are the same number. Okay, enough of that. What else?
56.
56. Let's see. 56. We've got, okay. So number 56, we have the sum, k going from 1 to infinity of 20 divided by 25k squared plus 15k minus 4. Okay. So the first question that I have here is like, can I figure out a way to factor the bottom? Because as is, I could start plugging in some values for K and stuff, but it looks like a mess. And so is there a way to factor what's on the bottom? Any thoughts?
Yes.
Okay, yes is a good answer. What could you do?
Factor by grouping.
By grouping?
Could you complete the square?
You could complete the square. Would that help us? I don't know.
The grouping?
The group, how do you want to group it?
Well, it would basically factor out the 25K squared minus 5K, and then it'd be 20K minus 4.
Okay, so let me pause for just a second. What I'm seeing is a 25 and a 4, which multiply to 100. So I need something that multiplies to 100, negative 100 actually, but adds to positive 15. Two numbers that multiply to negative 100 and add to positive 15. What are they? 20 and negative 5. Okay, so on the bottom, I have 20 and negative 5. So how is this going to work? Let's see, the 25 is either going to, this is fun. This is fun. Okay. So let's say that the 25 is on a K and a K is by itself. Just a second. Yeah, go ahead.
Negative 2%, negative 1/5. Does it like, I did quadratic, or not quadratic.
Oh, you did the quadratic formula.
Yeah.
That's good. So, okay, that's a good way to do it. So what if you use the quadratic formula to factor it? So that would be negative b plus or minus the square root of b squared, so 15 squared, minus 4 times a times c, which would give me plus 400.
Well, minus 400. Or no, yeah, plus 400.
Plus 400, I believe. Yeah, over b, sorry, 2a, thank you, 50. Okay, what's 15 squared?
225.
Yeah, 225. So this is negative 15 plus or minus square root of 225 plus 400 is 625. Is that a perfect square?
Mhm.
Yeah, what is it the perfect square of? 25, yeah, all over 50. So this is negative 15 plus or minus, this is 25 over 50. And what is that? So negative 15 plus 25 is 10. So that's 10 over 50. And if I did minus, what would it be? 40, negative 40 over 50. So it's either 1/5 or negative 4/5. Okay. So that means that gives me the answers for K. Is that helpful, what I just did? It's helpful, yes, but we have to decide how it's helpful. So what I'm saying is it's kind of sort of like K minus 1/5, K plus 4/5. But obviously that's not so great because that doesn't actually multiply together to give me what I have up here. But I have a feeling that it's like a multiple of these things. But what if I multiplied everything there by, let's say, 5. And let's just see what happens. Now, you can't just go around multiplying by 5, but obviously this is wrong. This is not the factorization. So let's say I put a 5 here, 5 here. If I multiplied this by 5, I'd just have 1. If I multiplied this by 5, I'd just have 4. Okay, so how does this work out? 5k times 5k is what? 25k squared. That seems good. -1 times 4 is -4. That seems good. 5k times 4 is 20k. Minus 5k is 15k. That's it. So getting these roots did actually help, but it was a multiple of what I got out of the roots. Does that make sense? So it was actually like my roots times 25. Anyway, if you like that, wonderful. So, and then on top, I still have 20. So now, does everybody buy it that this was actually not like the easiest factorization ever, but we got there, and that's the factorization. Now, is this in any way helpful? Yes, because now I could use partial fractions. Okay, I could split this thing up into 2 fractions using partial fractions. So let's do it. If I did, I'd get 20 divided by 5k minus 1 times 5k plus 4 is equal to a over 5k minus 1 plus b over 5k plus 4. You clear the fractions out and I get 20 equals a times 5k plus 4 plus b times 5k minus 1. All right, and now what could I plug in that would make life easier?
Yeah, minus 4/5.
Yeah, so I could plug in minus 4/5 or positive 1/5, right? Yeah, those seem familiar. So let's plug in minus 4/5 for x. If I do, then this whole term just goes away. And so I get 20 is equal to, that's 0. Then if I plug in negative 4/5 here, negative 4/5 times 5 is negative 4, minus 1 is minus 5 times b. And b is equal to negative 4. Everybody with me? So b is minus 4. Now let's use that x is equal to 1/5. If that's the case, that one goes away. And I get that 20 is equal to 1/5 of 5 is 1 plus 4 is 5a. So I get that a is positive 4. Okay, so now I can rewrite this summation. Let's just go right here. And this is equal to the sum, k going from 1 to infinity of, let's see, it's a over 5k minus 1, a is 4. So I get 4 over 5k minus 1 plus b, which is minus 4, so I guess it's minus 4 over 5k plus 4. If I really wanted to, I could factor out the 4 outside of the summation. I can, or I don't have to, either way. Okay, so now let's start plugging in some numbers for k and see if this makes my life any better. So let's say that I plugged in that k is equal to 1. What does this become? And don't subtract, just leave each piece alone. So if I plug in 1 for k, I get 4 over 5 minus 1, which is 4 over 4, or just 1 minus. Then if I plug in 1 here, I get minus 4 over 9, correct? Minus 4 over And again, don't combine them. That is not helpful. Plus, now let's plug in 2. I plug in 2, I get 2 times 5 minus 1 is 9. So it's 4 over 9. Minus, if I plug in 2, I get 10, 14. So it's 4 over 14. Let's do the next one. And I get, plug in 3, I get 4 over 14. Minus, this is 4 over, let's see, I'm plugging in 3. 15 plus 4 is 19. Okay, so 4 over 19. And so on, up to, if I went to the nth term, the nth term would be, I plug in and I get 4 over 5 n minus 1 minus 4 over 5n plus 4. And this is my S sub n, my nth term of the series. Notice now that things start to cancel out. So the negative 4/9 and the positive 4/9 cancel. The negative 4/14 and the positive 4/14. Da-da-da, da-da-da. And what's left over? S sub n is equal to 1 minus 4 over 5n plus 4. So this is how you would calculate the nth term of the series. But I'm interested in, well, what if n goes to infinity? So I can just take the limit as n goes to infinity. So the limit as n goes to infinity of S sub n. And that's going to be the sum of my series. But that's the limit as n goes to infinity of 1 minus 4 over 5n plus 4. So as n goes to infinity, what happens to the bottom of this fraction? It goes to infinity, so the fraction goes to 0. So that whole fraction goes to 0, and I'm just left with 1. So pretty crazy, actually. If you look at this summation, you'd think that is a mess. What does it add up to? 1. Kind of cool. And of course, what do we call this type of a series? A telescoping series. That's right. And why we call it telescoping is because of the old telescopes that you could like pull out long and then they collapse down. Same thing's happening here. You've got this long telescoping series and all of the things collapse down to just something very simple. Then you take the limit of the simple thing and you get your answer. Sound good?
So all telescopes are just the first and the last?
No, not necessarily. Usually telescopic series sometimes simplify down to many less things than there would be. Sometimes it's not just the first and the last though. Sometimes it's like there's a term here and a term here, and then there's like a couple terms at the end that need to be counted. It's not always just the first and last. You just have to kind of look at it. In this case, I could see that guys that are next door neighbors cancel each other. But sometimes it's not the next door neighbors. It's like you're 3 away that cancels. And then 3 away cancels. So you have to think a little carefully about it, about, okay, how does this collapse? So maybe instead of there just being 2 terms at the end after collapsing, there are 4. Does that make sense?
Yeah.
Okay. Yeah, so be careful. It's not always just the first and last. Yeah.
You number 20.
20? Sure.
Okay. So it says evaluate each geometric series 2 ways. First, find the nth partial sum and take the limit as n goes to infinity, and then use the theorem. Okay, and we're doing number 20. So we've got 2 4/3, 8/9, yada, yada.
So we've got 2 plus 4/3 plus 8/9 plus 16/27 plus, and so on. Okay, so first they say to find the nth partial sum, correct? And then take the limit as n goes to infinity. Well, the nth partial sum of a geometric, I wrote it before. First of all, maybe we should recognize what is A in this situation and what is R. That might be helpful. So A is always just the first thing. And then what do I multiply to get here? Get 2/3, and then 2/3 again, and then 2/3 again, etc. So A is 2, and R is 2/3. Agreed? Okay, well, what the book tells us is Sn for a geometric is A times 1 minus R to the n divided by 1 minus R. So what is that in this case? Well, A is 2. We get 1 minus R, which is 2/3 to the n divided by 1 minus 2/3. And then we could take the limit of that thing as n goes to infinity. But as n goes to infinity, what happens to 2/3 to the n? Yeah, it gets small. So this thing, if I take the limit as n goes to infinity of this nth partial sum, 2 times 1 minus 2/3 to the n over 1 minus 2/3, this guy just goes to 0, right? And I'm just left with 2 over 1 minus 2/3, which is 2 over 1/3, which is 6, right? And then the other way we could do it, so this is kind of your part A way. Your part B is just plug it straight into what is A over 1 minus R. And A is 2, 1 minus R is 2/3. So I just get 2 over 1/3, which is 6. So we could take the nth partial sum and take the limit, but that's just the same thing. And in fact, it's exactly the same thing, because when we take this limit, that just goes to 0, and we're left with our original formula, A over 1 minus R. Either way, we get 6.
So what's the benefit of doing the additional third, the limit, and goes to infinity?
Nothing. What they're trying to do is make sure you understand where this came from. Does that make sense? Like A over 1 minus R, it's not magical. It came from somewhere. Where did it come from? It came from taking the limit as n goes to infinity of this nth partial sum formula for a geometric series. So I think I derived the whole thing in the lecture, but I have a long formula. I multiply both sides by R. I subtract some things. Some nice things cancel, and you end up with S of n equals this. Then when you take the limit as n goes to infinity, wonderful things happen with this R to the n. It goes to 0, and you're just left with A over 1 minus R. So this really nasty geometric series condenses down to this like super easy thing to calculate, right? So geometric is kind of like the dream of series, of infinite series. It's so easy to compute geometric. So one of the first things you should always do when you come up against an infinite series, and we need to start developing our strategies, is you should ask yourself, is this a geometric series? Because if it is, It's so easy. And then a lot of times the answer is, nope, it's not. Like the one we did over here, it wasn't even close to being a geometric series, right? So that doesn't work. But if it does, it's wonderful, and it's just a over 1 minus r. So we like geometric series. Sound good? Okay, that's it for today. I will see you on, let's see, it's hard to remember what day it is even. This is Monday. I guess I will see you on Wednesday, and we will talk about the next section. Have a good day. Yeah.
Do you teach calculus
3? I'm not scheduled to right now for next semester, but honestly, the world is in chaos. So I don't know what I'm teaching exactly. I know some classes that I'm teaching for sure. I don't think I'm teaching calculus next semester, but I don't know.
Okay.
That's the best answer I can give right now.
Have a good night.
You too?
Do you have the test?
Yes, I do.